Hi everyone, I hope that you're enjoying the conference so far. So since this is a talk, we need to put some cats in the slides, so here it is. And this is also how I was when I thought about game programming in general, especially for the game that I'm gonna talk about. But let me show you, and I hope to show you during this presentation that you will more likely to become like this. Like this. Like, you can do it. It's accessible for everyone. And this is the story, my story, of how I ported Doom to the browser thanks to WebAssembly. So, first I present myself. Hi everyone, bonjour, marhaban. I'm Yassine, I'm a DevRel engineer at Worldline. I'm a teacher. All my lectures are open source on GitHub. It's a little, some lecture notes are a little bit messy, but please take a look. It's all available on GitHub. I'm also an organizer of the Lille Android user group. And I so happened to collect some video games, which also motivated me to do this project. So I'm part of Worldline, which is a paytech company. It's not located here in Tunisia, but we have offices all over the world. But I'm more here to talk about the technical stuff that we share. I am part of the team that maintains our technical blog and the YouTube channel. So I'm kind of a YouTube administrator, if you can see it like that. There are interesting talks in our different websites. Some things that we have seen earlier, for example, soft skills, technical skills. So please take a look if you want to learn things and see our presentations on our technical articles. Okay, let's go back to the presentation. Since I'm giving you my story, so let's start with a prologue about WebAssembly. Do you know about WebAssembly here in the room? Can you raise your hand if you have heard about WebAssembly? Okay, nice. Thank you. So WebAssembly is a very powerful technology. It's a portable binary instruction format. You can see it like a JVM, which runs everywhere, but with also some more interesting features. So you see in the bottom side of the screen how it looks like. It's really a binary. But what's really interesting about WebAssembly is that it runs on browsers and even outside browsers. For my work, I just focus on the browser side, more precisely like this. So we have the browser on the right, which runs WebAssembly code. But what's also interesting about WebAssembly is that you don't need to write WebAssembly code. You can write first your code in any high-level language that supports WebAssembly. For example, here I've put C#, I've put Kotlin, C++, Rust, or any language that compiles into WebAssembly. And then you have, as long as you have what we call a compiler, a WASM compiler, or a WASM toolchain. The most famous one is Emscripten, but there are many more depending on the language. And once you compile your code into WebAssembly, you will have your WASM binary and some JavaScript glue code. It allows, the WASM code to interact well with your browser. And once you have this, you just need to load your WebAssembly file and your glue code into the project, and you have access to another language in your web application. So WebAssembly has the reputation of being faster than JS. It depends on which projects or on which code you write. But for me, the biggest advantage of WebAssembly is that you have access not only to JavaScript, but to all languages in the browser. So that's a very promising technology, and WASM has other features. For example, it can be used as a containerization technology. You can create containers with WASM, for example. But this is another topic. I'm just really focusing on the browser aspect. So once I saw this, I understood that the possibilities are limitless. It opened a lot of new doors to web development. That's why I started to compute, to imagine ideas, and do something related to WASM. I was really eager to try something related to this technology. That's when .NET added support to WASM, and that's when the initial idea started. So .NET is a framework like the JDK, like Java JDK, but its language is C#. It's open source, and it's cross-platform, Windows, Linux, Macs, desktops, mobiles, and so on. And recently, it added the possibility to compile into WebAssembly through two means. The first one is Blazor WASM, which is a web framework like React, Vue, or Angular. Instead of writing JavaScript, you write C#, which is compiled into WASM. So you have this possibility. But for this kind of project where you develop a video game, you want to start with a vanilla frameworkless. That's why you have WASM tools, which is more a vanilla approach. If you want to write C# that communicates with your, that runs as a WebAssembly. So let me show you how it looks like. So this is an example of Blazor WASM. You have some HTML and some C# at the bottom, and both interact together. So for your information, this was the only way to run WebAssembly in the beginning of the WebAssembly support in C#. I made my project run thanks to Blazor WASM, but it was a little bit tricky. But after that came a new way to run WASM with C#, which is called WASM tools. And as you can see here, it is a more natural way of communicating between JavaScript and C#. So you see here that we export we export C# functions into JavaScript, and we can call them from the JavaScript side. So the top is C# and the bottom is JavaScript. And you can do the opposite way. You have some JavaScript code that you export, and you are able to import into the C# code. Let me show you a small video to show you how it works. So we are on VS Code, and here we install the prerequisites. It's just some additional tools that allow you to write WebAssembly to compile your C# into WebAssembly. After that, you create a project from a template. So just by running this command, you get all necessary files and a starter project to write WebAssembly code in C#. And after that, you can open the main C# file, which contains in this sample, a timer. So every second, the timer is updated, as you can see here. So the stopwatch.render updates the timer. And this is what is done in C#. So it's a timer, and it calls set inner text, which is a JavaScript function. So it calls a function exported from JavaScript, which updates the DOM, the document object model. And it exports some functions so that they can be called in JavaScript. On the HTML, on the web side, your HTML file is a regular HTML that loads the JavaScript file. And the JavaScript file exports the setInnerText method, and the implementation is here. It's called from C#. And we also load all the exported code from C#. So this code is compiled into WebAssembly, and you can call it from JavaScript. So it's two-way communication between C# and JS. Once you're ready, you can run the server with just by running .NET run, similar to npm run start. You have a local development server. You open it, and you have this kind of application. Where you have the stopwatch, which is managed by the WebAssembly part written in C#. So this is a quick demo to see how it looks like in a small project. So when I saw this, and since I'm a game collector, I wanted really to port a video game thanks to this technology. So the idea is to start with a C# game and make it run on the browser. That's when the idea of Managed Doom came. So let me first talk about game porting. The game porting is the act of making a game run on a platform other than the original one. Mainly, there are two ways to do it. Either you do a full rewrite of the game from scratch, but what is usually done is to take the source code of the game in the original platform and adapt it or rewrite it into the new platform. And this allows to have something that runs very quickly, even though sometimes it's not fully optimized 100%. Maybe that's what you notice in some games. When they are run in multiple platforms, some platforms are worse than others. And what is not considered as porting is using a virtual machine or an emulator. Of course, because a virtual machine simulates the original machine, so it's not porting. And what served me as a reference is MVG. He's a YouTuber who is famous for writing Switch, homebrew in general, and now he's a video game developer, and he shares a lot of insights, a lot of tips on video games in general, and in one of his videos, he showed how he ported Heart of Darkness, which is a great PlayStation game, and he showed how he ported it into Windows. And that's what gave me the idea and gave me the, how to say it? Yeah, he made me change my mind about game porting. I thought that it was something impossible for big games, but in reality, it's very easy. I will show you how I did in the next slides. So my choice was the Doom game. It's a very famous first-person shooter, one of the first first-person shooters. It was released in 1993 for DOS. And it was really interesting because it rendered 3D graphics using simple 2D technologies. There was no 3D cards at the time. And it was also very well architected because it separated the engine, which updates all the game logic, the game state in its source code, but the graphics, the audio, and everything not related to logic is placed in a WAV file for visual data and in an SF2, which means sound font, for audio data. Meaning that Doom is portable by design. Why? Because you just need to rewrite or port the engine into the new platform to be able to run any Doom WAD or any Doom sound font. And indeed, there are many ports. So you see here some official ports of Doom in many consoles, and they happen to have 3 cartridges on the right. So they're on Super NES, on Game Boy Advance, and on Nintendo 64. But there are many more ports, and there are even exotic ones, as you can see here. Especially the piano, it looks very fun. You play Doom on a piano. And there are many, many more. So what I did for my project, I didn't start from the C source code of Doom. I started from an already existing port of Doom. So id Software released the source code of Doom in C, and then a GitHub user called Sinshu released a port of Doom in C# that runs only on desktops, which is called Managed Doom. And it uses the SFML library. SFML is a library which is written in C. It's also available in C#. It allows to, it's similar to SDL. It allows to render frames, play audio, interact with the user input, but it's not available on browsers. So what I did is that I forked this project and I made the game run on browsers by replacing the SFML stack. So this is how the strategy or the agenda or the plan that I followed to make the port. And you will see it's very easy, it's very simple and accessible to everyone. So what I did first is to clone the Managed Doom repository. And as the first presentation said of the day, it's okay to copy because here I'm trying to bring something new, to learn, and to have fun. And I changed the build target to WASM, not desktop, but WebAssembly or browser WebAssembly. And there are 2 major things to do. The first one is to re-implement the SFML code. I started by writing mocks, meaning that I just reproduced the function signatures, the class signatures, without writing any implementation. And then, once it compiles, by doing some guesswork, some reverse engineering, implement the corresponding functions. And the second big thing to do is to delegate or relegate to JavaScript side some things that you can't do in WebAssembly. I will show you, so the 3 parts that were done in JavaScript is the game loop, the rendering, the displaying the frame, and playing the audio. I will show you this later. But let me give you one example of each category. So first of all, let me show you so before this, so as you see here in this monster, when I was doing the project, I was not like this, to reassure you. I was not like having red eyes, not sleeping. It was really fun, and it was really joyful experience because I started from scratch. I didn't know anything about the DOM engine, the source code, how it was developed, how it works, because game porting doesn't require you to have full knowledge of the project. As long as you have something that compiles and runs, it's okay. So this is an example of something that was relocated to JavaScript. The game loop. Any video game runs in an infinite loop, which is called for every frame of the game. So for a 30 FPS game, this loop iterates 30 times per second. And for each iteration, we get the player input, what he pressed in his joypad or keyboard, and then we update the game state, the position of the player, the position of the enemy, the HP of the player. All this game state logic is updated after getting the input. And this allows to generate a frame and the audio to play for that frame. And then it's just the rendering of the frame and playing of audio to have the image and hear what's happening in the game. So the infinite loop is not possible in JavaScript. You know, JavaScript is single-threaded. There is a better way to do this, and which is called request animation frame. So as you can see here, we keep the same logic inside the loop, but we replace the infinite while loop with a recursive call to request animation frame. So this is a browser API. This is available on browsers, and it allows to paste the frame in an optimized manner. For example, when you switch tabs, the request animation frame method isn't called. So when you switch tabs, when you don't use the tab, this function is not called, meaning that your game won't run and meaning you're optimizing your battery life. So it has this kind of interesting features. Now let me show you another example of the porting the SFML library. For example, here, this is some code in the managed DOM source code, which makes use of the sound buffer class. This class is not available in WASM. It's available in SFML, which is not available in the WASM target. So what I did is that I rewrote it simply. I just create a new class which reproduces the same signature, the same package name, and also with some reverse engineering, or by just viewing the code and understanding the code, reproduce the arguments of the constructor. So first with a mock until it builds, so empty implementation. And once I have the project which is building, I started implementing missing features to have something on screen and to hear some audio. And this is the final implementation. You see that it's very easy, very intuitive. And many functions have been implemented like this. Many missing features not available on the WebAssembly target have been implemented by just gluing, adding some glue code, and that's it. So very easy and very, it's much easier than I thought. So to summarize, the game that I started from, the managed DOM architecture, it has a for loop, which sends the user input into the DOM engine, which iterates by one frame, and it has a WAD and a sound font as input to generate the sound and the audio. This DOM engine generates a frame buffer and an audio buffer, which is then sent to SFML to be rendered on screen. And this is iterating indefinitely. Fortunately for me, 70% of the code was already WASM compatible because the game engine doesn't interact with, doesn't render frames, doesn't play audio. It's just logic, pure logic, which is cross-platform. But I needed to port the top part and the bottom part. That was the most challenging part of this project. But it was really fun because it allowed me to learn new things, new JavaScript APIs. So request animation frame, as I showed you, and also AudioContext and the Canvas APIs, which are very powerful APIs in the browser. I really recommend you to take a look at what you can do with them. And there is also one interesting thing is that you see the colors. So the green rectangles are JavaScript side, and the purple rectangles are WASM or C# side. So there is also some interaction between the two parts. And it's done thanks to the framework does the interaction, but behind the scene, it's marshaled data. So sometimes it's JSON, sometimes it's an array of bytes that is sent between one to the other. But fortunately, it was very optimized. It doesn't impact performance too much. So let's take a look at some code. That's why the screen becomes darker, because there will be some code. So as you can see here, the entry point is what I showed earlier. You have a canvas and the JavaScript file which loads the WebAssembly code. And the game loop is run in the main.js files here, the main.js file, sorry. So here we import all the code exported from C#, and one of the methods exported from C# is the update game state. This is the main engine that the main function in the Doom engine that advances one frame in the game logic. So it updates the player position, the enemy position, the player HP, and so on. Everything is updated. And inside this function, there is also a call to draw the frame and to play the audio. And I will talk about it in the next slides. So this is the implementation of the update game state, which inside of it, so advances, as I said, updates the game state and renders a frame and plays the audio. Talking about audio. So as you know, an audio or a sound effect is just a wave. And to store it inside the computer, we do what we call sampling, meaning that we get the value of the wave at regular intervals, which is called the sample rate. And what is, and this is done already by the Doom engine. So this, I didn't touch it. I already get, thanks to the Doom engine, the frame, the audio buffer, and the sample rate. What I did was send this to JavaScript and implement the audio context, and implement an audio context to play this, audio buffer by giving the sampling frequency. This is the code that achieves this. So this is the code that allows to send the audio buffer to JavaScript. So the audio buffer is already computed by the engine. I didn't touch it. I just sent it to JavaScript. Hey, play it for me. And this is the code that I implemented to play the audio buffer. It's state-of-the-art audio context APIs. You can go to any tutorial on the internet. This is how we use the audio context in JavaScript. One thing that I had to do in particular here is to normalize the samples, because the Doom engine sends the value of the wave from minus 256 to plus 256, or maybe a little bit more, but I normalized to be -1 to +1. One other thing that I did, so the audio and the video are displayed correctly in the demo that I'll show you later. So to render a frame, I also implemented some custom JavaScript code to render a frame. So the Doom engine generates this one-dimensional array, which contains not the RGB values of each pixel, but since it's an old game, you know, in retro gaming, we used a lot color palettes. It allows to reuse a color many times instead of having to code each color in each pixel differently. For example, here, the value 0 for the first pixel, meaning that the first pixel will be red, like this. And the 1 meaning that the second pixel will be green. So the question that I ask you, how the pixels will be spread in this array. So it's not from left to right, top to bottom. I tried this, it didn't work well. It was spread like this, from top to bottom, from left to right. The question is why? Because this is related to the Doom engine itself. So the Doom engine renders, I told you that, as I told you, the Doom engine doesn't use 3D technologies. It uses a technique called raycasting, which renders each column like this. It sends a ray on each column of the frame to render it like this. So that's why the pixels are laid out from top to bottom and left to right. And when I laid out the pixel from left to right, top to bottom, I got a very ugly image. So this is the code that renders a frame. So similar to the audio, the frame is already computed by the engine. I just needed to send it into JavaScript. And this is the JavaScript code that draws a frame. So here it's also state-of-the-art canvas usage. So here we distribute the pixels from top to bottom and left to right. So we first we increment the index y before incrementing x. So we go to the line by line and then column by column. And for each pixel, we draw it like this. So extract the color from the color palette, and then we put the RGB values in each element of the canvas. Because in the canvas API, so a pixel is 4 elements of the array: the red, the green, the blue, and the alpha. So that's for the technical part. So now, as we say, après l'effort, c'est le réconfort. After effort is recomfort. Let's play some Doom. So please take your phone, scan this QR code. Just put your phone in landscape mode, because it's better optimized to be in landscape. So scan this QR code and put your phone in landscape mode. It should work on any phone model. It's WebAssembly, it's standard web technology. It should work even on iPhone, and you even have your a tutorial on how to use the different prompts. So this is, it should work at 30 frames per second. And this made it work in like after 1 or 2 weeks of personal time work. To make a game like this run, this is the power of porting games. You can make things like that run very easily. So here is the game also on my Mac. And as I told you, you have even the possibility to load other WADs. As I said, Doom separates the engine from the graphics. I also provide 2 free WADs to avoid any legal problems that you can play also on your browser on the go. Now, and what happens when I switch tabs? Thanks to request animation frame, the game is paused automatically, because request animation frame doesn't run when the tab is not active. And now, this is the end of my story with some key takeaways. WASM possibilities are limitless. It's not just making JavaScript faster. It's not just replacing or adding another technology to create containers. It's limitless. You can make video games. You have access to a lot of possibilities. We are just limited by our imagination. And also, game development in general and porting a game in particular is a way to learn programming while having fun. I really had fun during this project, especially when I had such a game like that made my childhood, that I played a lot during my childhood. Having it work while trying new things, learning new things, was a very fun experience. So thanks everyone for your attention. Thank you.